All right, so this is our last lecture for the semester, right? So let's get to it. So we're going to finish up the rest of chapter 10, which is just section 10.5, finishing up with the heat equation. But before that, let me just give you an update on what we have coming up. So I'm going to hold a review session. So I will have review sessions next week. So you'll have the weekend and Friday to do as much as you can. I posted 2 final exams on my website, so if you can work through those exams, that would be great. So when you come in to the review session, we can just quickly go through the ones that you have trouble with. Okay, so you'll find the PU Fast final exams on my website, and there are tons of them on the mathematics department website as well, so you can look over those as well. So there's going to be a review session next week. So I will hold one on Monday. So we'll have one on Monday the 20th from 5 p.m. to, let's say, 7 p.m., 2 hours. Hopefully that's good enough, but if you guys want to go a little over, a little less, that's up to you guys. So come in with questions, and this is going to be through Zoom. Okay, so it's not going to be on Blackboard, it's going to be through Zoom. I will send you guys the meeting ID and the password. That way you can download Zoom app or use your laptop or whichever device you like. Come in using the meeting ID and the password. So the link will be sent to your email, and we'll have a second review session on Tuesday. That will be the 21st, and that will also be from 5 to 7 p.m. So same thing, it will be on Zoom. So I'll send you a link. So the ID and password, I think that's what it requires for you to join. So that will be on your email. Okay, so any questions on that? So please try to speak through your audio, that way it's quicker for me to respond to you. No, you do have to submit your work for the final exam, just like you've been doing for the exams. I will open up a link on Dropbox for you to submit your work for the final exam. So I'll write all of that out in an email, because right now I want to finish the course. So, and if we finish early, I'll just write it out at the end. But Sadia, remind me either through an email or at the end of today's lesson, okay? So thank you, Sadia, for bringing that up. So yes. All right, thanks a lot for bringing that up. Driss, do you have a question? So the reason I didn't upload is because my notes, because I'm writing it on a darker background, when I convert them to a PDF, you can't see all of them. So that's why I'm not uploading any more notes. So just the videos. But you can still find my lectures on a YouTube video and then probably just copy it down from there. I think it's best. No problem. All right, so that's the update I have, and we have our final exam scheduled for, as I mentioned, what was the date I gave you guys? Forgot. 23rd. Yep. Thank you. July 23rd, 2020, and this is going to be from 5 to 7:15 on Blackboard. So make sure you are there to take the final exam on this day, so don't miss the final, right? That's like 50% of your grade, so be there on that day. All right, so having said that, so I will also record the review session and put them up on my YouTube channel. You guys can look it up. So that that will be there for you as well. It's just the notes I'm not posting because they just don't come out great as I want them to be. So I guess videos are better. All right, so let's start. So we were talking about last time. Ooh, I have a question waiting for you. Let's wait. Let's keep it waiting. So we were working on 10.2 and 10.4. I hope you guys had some homework questions to work on. I was looking on WebWork and I noticed that there is no question on Fourier series on WebWork. So I don't know why that's that, but whatever the reason is, you have the textbook as your resource. Look out to the textbook questions for 10.2 and 10.4. Do those as a practice. And then start looking at past finals. Those are great practice too. So on WebWork, so I should also mention that. For WebWork, there are few sections that are called EC. So there's EC1, and then there was EC4 and 5. You can skip those. They're somewhat irrelevant to the course, and I don't really like those for this course. So skip those. I'm not counting those. So the one you should be finishing up are the rest of chapter 10, homework 20. I think that's also called homework 20 on WebWork. Finish those up, and then chapter 6. Those are the last assignment you need to do. Once you finish them, just start reviewing for the final. Alright, so having said that, let's continue with where we left off last time. So we're working on Fourier series and odd and even functions. So if we revisit our notes from last time, I kind of wrote down what is an odd function and even function, and we talked about if the function is odd or even. So let me see which one I gave you last time. So I gave you this one. If the function is odd, then the Fourier representation will only involve Bn, because a0 and an will go to 0. So those coefficients are 0, so you'll only have a Fourier sine series representation. Now, continuing from here, so this question needs to wait a little bit more. So continuing from there, now here's the next remark. You can think of it. If f of x is even function, then which coefficient is going to be 0? So if it's even, you guys should think that Bn is going to be 0, right? Because you're integrating an odd function, which is sine, an even function, f of x. So even times odd, you will have an odd function. And if you're looking at an odd function over a symmetric interval, the integral goes to 0. So therefore, Bn is 0. So you can verify this. So f of x can be represented as Fourier cosine series. Okay, so your Fourier series for this function would involve a0 over 2 plus the sum n from 0 n from 1 to infinity an cosine of n pi x over L. So that will be your Fourier series representation for an even function. So these are very useful tool to have if we're looking at a particular function such as odd or even. Okay, so this is for the even function. For the odd function, I wrote it down last time, so you'll have a Fourier sine series representation. So based on these two knowledge, we can extend our function as an odd function or an even function. Okay, so there's two types of extension we can do for Fourier series representation. So we have two types of extension. So sometime the question will tell you what kind of extension they want you to do, sometimes the function itself should tell you what type of extension you're supposed to do. Okay, so you take the period of 2L and then you extend it either odd function or even function. So we can extend that as an odd function or even function. And if it's neither, then your function for the Fourier representation, you'll have both an and bn to survive. So that's another thing to remember. Now, based on all of that, here's an example that we can work on. So let's call this our first example. So for this problem, we want to find the Fourier series for the function f of x equals x squared on the interval -1 to 1. So let's see if this is an odd function or even function. Based on that observation, we can cut down some of the calculation and compute only the one that we need. Okay, so we don't have to compute everything. Let's graph this, because graphing would help you to understand what kind of extension you're going to do. So f of x is x squared on the interval -1 to 1. So if I plug in -1 into the function, we get 1. And if I plug in 1, we also get 1. So this is f of x. Right? Now, so here you want to step back and decide, is this an odd function or even function? So this is 2L, 1 period. So someone tell me if this is an odd or even function. It's even. So that means we can extend this as an even function and only compute Fourier cosine series because bn will go to 0. If you were to do the computation, you'll get 0 for bn. So if we extend this as an even function, that's how the picture would look like. So again, my drawing is not the best drawing. You can always look this up in the computer and see how to graph this and just keep repeating, right? That's the extension of this function of period 2L as an even function. Now what is the Fourier series going to do? Well, Fourier is going to smooth out all the edges and create a very nice wave that will approximate this function and be very close to it. So it will create these wave, something like that, and just smooth everything out. Very smooth wave. And the more terms you add to your solution at the end, better approximation you'll get to the function. But our concept is to find those coefficients, write out the representation. So because it's an even function, right? Because f of x is even, we only want to find a0 and an, and bn it's going to be 0. So there is no need to compute bn. Okay, so let me know if you guys have questions. So from the definition, we know a0 is given as 1 over L integral from -L to L f of x dx. Now what is L for this problem? So this distance right here is 0 to L. So you know L is 1, or you can think of L is the entire 1 period. So you can think of it as 2L is equal to 2. So that would give you L is equal to 1. So you can also do it that way. So we know L is 1. So f of x is x squared. And because f of x is an even function, I can double this integral and just go from 0 to L. So we're going to double the integral and go from 0 to L of the function f of x dx. So again, I'm using the properties of even functions to simplify the calculation. So now let's continue. So we have 2 over L, L is 1, 2 over 1 times the integral from 0 to 1, f of x is x squared dx. And now we go ahead and integrate. So we have 2 times x cubed over 3, taking it from 0 to 1. If we evaluate this integral, this is 2 over 3. So that's a0. Now the next coefficient we need is an, and then we have our Fourier representation. So what is an? By definition, an is 1 over L, integral from negative L to L, f of x times cosine of n pi x over L dx. Now again, we're going to save some time by using our properties of even functions. So f of x is even, cosine is even, even times even is another even function. So that means I can again double the integral and go from 0 to L of the function f of x, cosine of n pi x over L dx. And now let's substitute our unknown variables L and f of x. So we have 2 over 1 times the integral 0 to 1. F of x is x squared, cosine of n pi x, L is 1, dx. Oh boy, so how do you integrate this now? Big question. What method are you guys going to use? Yeah, right, this is a by parts. But we're going to use tabular's method to save time. So using tabular's method, so let's do that on the side. So we pick a column for the derivative, which is u, and we pick a column for dv, and we just integrate. So let me just write it, not this way. So we pick a column for the derivative, we pick a column for the integration, and we just put them together. So we have x squared, differentiate 2x, differentiate 2, and differentiate until you get 0. There you go. Now the next column we're going to integrate, so that's cosine of n pi x. So if I integrate the first time, I get 1 over n pi, because that's a constant, sine of n pi x. Now if I integrate one more time, I get negative 1 over n squared pi squared cosine of n pi x. And if I integrate one more time, because I need to get to the 0th level, that's negative 1 over n cubed pi cubed sine of n pi x. And then we just cross them this way, and then we multiply them with plus and minus sign. So we have our integration for this, and that was the shortcut to by parts. So we have the product of x squared times 1 over n pi squared sine of n pi x going from 0 to 1. And the next one we have is minus. So the minus from the integration will cancel out, so that's plus. We have 2x over n squared pi squared times cosine of n pi x going from 0 to 1. One more. Plus, well, it's going to be minus because of the negative sign we have from the integration. Negative 2 over n cubed pi cubed sine of n pi x, again taking it from 0 to 1. Alright, so the difficult part is done. Now just evaluate this. So if we evaluate this, what do we get? So something nice should come out of this. So check this out. If we plug in 1, the first term, plug in 1 for x, that survives, but the sine of n pi goes to 0. So if you plug in 1, the first term will go to 0. And then when you plug in 0, so I am looking at, where am I looking at? I'm looking at this integration and I'm evaluating the top limit and the bottom limit. So when I plug in 0, that's also 0. Cool, right? That looks like an emoji. 0 minus 0 is an emoji. Okay. And then the second integration, second result we have, so now I'm looking at this one. If I plug in 1, it survives, right? We have 2 over n squared pi squared times cosine of n pi. What was cosine of n pi from yesterday? So that was negative 1 to the n power, right? Because cosine alternates between 1 and negative 1. So this would give you negative 1 to the n power. And if I plug in 0, the bottom limit, it goes to 0. So minus 0. And now the last one, we have is, so plug in 1, it will go to 0, right? Because sine of n pi is 0. Plug in 0, that will also go to 0. So what do we really have? So looks like I made a typo, guys. No one caught it. So all of these gets multiplied by the 2 on the front, right? From the integration. So that means all of this will also get multiplied by 2. So that was coming from the integration. We had it before. So if I just rewrite this, this would be 4 times negative 1 to the n over n squared pi squared. So that's our an. So we have the coefficient we want. We have a0 and an. Bn goes to 0 because we're looking at an even function. So if you do the work for integration, eventually you'll get to 0. So there's no point of wasting time on that. So we're ready to write out our Fourier series representation for this function. So we found a0 to be 2/3, and we found an to be that formula. So our function can be represented as a0 over 2 plus the sum, n starting at 1 to infinity, an cosine of n pi x over L. And bn is 0, so we don't need that term. So what do we have? We have f of x is equal to a0, 2 over 3. Okay, so that's 2 over 6, which is 1/3, plus the infinite sum, n equals 1 to infinity, of an. Well, an is negative 1 to the n times 4 over n squared pi squared times cosine of n pi x, because L is 1. So that will be the Fourier series representation of this function. Any questions on this? Does it make sense, guys? All right, so that's the idea with Fourier series. Now let me start you off with another problem, but I'm not gonna finish. You can do it on your own time. Okay, so suppose you have this example. So what if you had this example? F of x is equal to 2 on the interval 0 to x less than or equal to 1. Okay, and we want to find Fourier sine series. Okay, so the question itself is telling you which coefficient survives or not, right? So if you're only looking for Fourier sine series, what kind of extension are you going to do for this function on the interval of 2L? So, right, so we're going to, right, thank you. So we're going to do an odd extension, because only an odd extension will give us Fourier sine series, because you want the cosine terms to go to 0. And because of that, we know a0 will be 0, and an will be 0, and bn is what we need to figure out. Once you have it, you write out the Fourier sine series expansion. I will do the drawing for you, and then you can do the computation on your own. It shouldn't take you too much time because the function is very simple. It's just 2. So hopefully you guys can figure this out on your own. So if I were to draw this function, half of its period, 0 to 1, it's 2. So that's right here. It's just the horizontal line at 2. So if I want to extend this as an odd function for 2L, right? So we're going to extend this. That means it'll be right here at negative 2. So that will be an odd extension. And then you just replicate this period over and over to have the extension as an odd function, and then compute its Fourier series. That will be your job to figure out, so you can finish this. So any question how to do this problem? Right, so I take that as a no. Let me give you another example, okay? Again, you can finish it on your own. So take the same function f of x equal 2 on the same interval 0 to 1, okay? And I want you to find Fourier cosine series. So how would you start off this problem now? Absolutely. So we need to find a0, an, and bn, we know it's going to be 0. So you'll have a Fourier cosine series. So similarly, if I were to draw the extension of this, first I'm going to draw 0 to L. So this is 0 to L, okay? Just in case you're wondering what is L. That's L. L is 1. So from 0 to 1, we have the function 2. And if I want to extend this as an even function, well, the other half of the function is just reflected over the y-axis. So my drawing would just look like this for the even function. And then you just replicate this over and over so that you have more than one period. So we can extend this on the left side, and then we can extend this on the right side, and so on. So we can replicate more periods, and then the Fourier series will just be, it's cool. It's going to be nice. You'll find out. So you will write out what is that Fourier representation for this. So you'll fill in the rest, okay? The rest is just integrating and plugging them into the definition of a Fourier series. So hopefully you can take care of this on your own. And if you want me to finish the work complete, and maybe you can check your work with me, come to the review session. I'll be there to work these questions out for you. But for now, we're going to move on to 10.5 and finish up the course. So 10.5. 10.5 is the next very exciting section for this course. I mentioned to you guys, this course is it's really nice. It just takes materials from so many different variety of flavor, and you just add everything and tie everything together to get a really beautiful solution for that specific equation. So it's really nice course. So what is 10.5? So our focus for 10.5 is separation of variables. And so this is separation of variables for PDEs, partial differential equations, and the heat equation. So we're going to study a partial differential equation in this section. So all this time we've been working on ODEs. Now our focus is finally on a PDE, specifically the heat equation. So there's three major equations that you study in a PDE course. So if any of you are interested majoring in mathematics and study further graduate level of mathematics, you will see that PDE is one of very essential course, and it's very interesting as well. So they study three major equations in that course. So we study the heat equation. That's like the most well known, the heat equation. Yep. Thank you. All right. Hello, everyone. Is this better? Yep. Okay. Thanks. Let me know, okay? So we have the heat equation, which we're going to study in this course. And then there's also called the wave equation. That's also another very well-known partial differential equation. And there's also the Laplace equation. So it's not the Laplace transform, it's the Laplace equation, but it's the same Laplace, that same person. So these are the most fundamental, I would say, partial differential equation. There are plenty others that we study, but these are ones that you can look into and be more fascinated with PDEs. Our focus is on the heat equation, so let's get to that. So here's a scenario that I want to show you before we start writing what is the heat equation. So suppose you have a solid rod, okay? So I'm going to draw a picture. So here's a rod. It's parallel to the x-axis, okay? And so here's the rod. It's right on the x-axis, just for a better direction. And what we're going to do, we're going to heat the rod up, okay? So we're going to heat it up. So let's put some flame. Ooh, I guess yellow is good for flame, right? So we heat up this rod, so the heat is distributed throughout the rod. So it's going to be distributed evenly. So it's an ideal scenario, okay? And it's insulated, so the rod is insulated. So it means that the heat is not going to escape. It will remain inside the rod. And it's uniform, and the material that the rod is made out of is also uniform. So we want to study the heat conduction for the straight bar, or a rod if you want to call it, in a uniform cross section. So the cross sections are like this. So if you take a cross section here, it's going to be the same shape as the cross section on this side. Okay? So what do we want to know? Well, we want to measure what is the temperature at any given time and position. Okay? So U of xt would give us the temperature at any given time and position. So what do we want to know? Well, we want to find what is this function u of x variable and t variable, which will describe the temperature of the rod temperature at any given time t and position x. So position. Okay, so that's what the solution would do for us. It will describe the temperature. Now we want to find the temperature change or cooling off over time. Now what is the differential equation that governs this scenario? So the differential equation that we use to model this particular scenario is given by this equation. U sub t is equal to alpha square u sub x. So that's the differential equation, where alpha square is a thermal diffusivity. Okay, so this constant will be given to you in the problem. So this is always given to you in the problem. So based on the material, of course, alpha square will change because different texture will have a different diffusivity, right? So a different rate. And so it's just a constant. So you can just think of this as any constant. All right, so having said that, so we have our PDE. Now, what do we want to impose? We want to impose a boundary condition to this. So going back to this rod one more time, we're going to say this boundary is equal to 0. And on this boundary is equal to L. So the length of this bar is L. Okay, so L is just any real number. So we're going to impose the boundary condition U at 0 at any time t. It's going to equal to the boundary condition on L anytime t is 0. So we're going to restrict both boundaries to be 0. So both endpoints are 0. And we're going to let t be positive all the time. So this is the boundary condition B, C. And we're also going to impose an initial condition. So we have, now x could be anything, right? And we want time to be 0. And that would be governed by some function f of x. And x will only run from L to 0. So this is our initial conditions. So altogether, we have a partial differential equation to solve. So usually that's how you'll be given a partial differential equations. And what do we want to know? We want to know what is the function u of x and t that would solve this PDE. So we want to find solution to this PDE that would satisfy the initial condition along with the boundary condition. Okay, now what is the solution to this? I will show you the derivation, how to get to the solution, but let me just give it to you right now. So this is like the wow moment, okay? So just hold on to all of your thoughts until I show you the derivation where all of this is coming from. But for now, let's write it out, okay? So the solution to this boundary value problem and initial condition. So we applied all of that. We have u sub xt is equal to the sum from n equals 1 to infinity of bn e to the negative alpha square n square pi square over l square times t sine of n pi x over l. So that's the magical solution to this. Not magical, but that is the solution. And I will show you the derivation, so I'm not just giving you the formula. But this is the formula you want to remember for the heat equation. So for heat equation, for any given alpha square, any given initial condition and boundary condition is always 0, so that would never change. For any given initial condition, this would be the solution to the heat equation. So let me show you where this is coming from. Okay, so here's the illustration. So why, right? Why is, it's like the question you're asking, why is that the solution to the heat equation? Well, let's show. So we're going to use the method of separation of variables to find the solution to this. So the method of separation of variables. So just like we did for ODEs, we're going to use the same idea for PDEs. So we're going to start off with assume the solution to the PDE is u of xt, which is a function of x and a function of t. So we're assuming that's how the solution would look like. It has a function of t and a function of x. So just to simplify our computation, I'm just going to write x and t. So x is a function of x and t is a function of little t. Now, well, what does our PDE involve? Well, our PDE involves u sub t, which is the partial derivative of v with respect to t, and it involves u sub xx, which is the second partial derivative with respect to x. So we need to compute this derivative if we assume that this is the solution form. So we take some partial derivatives. So u sub t is going to be, so now x is a constant, t is the function. So this would be x t prime. And then, so now we need to compute ux x, right? So you go through the first derivative respect to x, and then second derivative respect to x. So you have x double prime. Now t is a constant. So that's u sub x, x. So then now we plug this into our PDE. So now plug into the given PDE, we have so that was ut is equal to alpha square uxx. So let's plug those in. So we have x t prime is equal to alpha square x double prime t, right? So just plugging it in. Well, now here you want to use separation of variables. So from here, use separation of variables. So we're going to isolate the x on the one side and t on the other side. So if I do that, I have the following. So we have t prime over t is equal to, so I'm going to keep alpha squared with t just to simplify things. Okay, it's just a constant. It can go with either t or x, doesn't really matter. I'm going to keep it with the function t just to simplify things more. You'll see why. So we have then x double prime over x, right? So we have successfully used separation of variables. Well, now you see you have a function of t variable, function of x variable, they're equal to each other. The only time these two functions can equal to each other if they're constant, right? So we're gonna let it be equal to some lambda, where lambda is a constant, because that's the only time this statement can be true. So then what do we have? We have two ordinary differential equations. So now we have two ODEs. So what are those ODEs? We have t prime, so this is the first one, t prime over alpha square. So let me just rewrite this. Alpha squared t is equal to lambda. And the second ODE we have is x double prime over x is equal to lambda. Two ODEs. Now we're just going to solve them independently, find their functions, and then just plug it into our assumption, which is x of x and t of t. Plug those in. But now here's the thing. We really have to think about this. Alpha can be any real number, right? It could be negative, positive, even zero. Well, what are those scenarios as we break these down into different cases? So let's consider the following. Consider the following cases for lambda. So what if lambda is greater than 0? What if lambda is less than 0? What if lambda is equal to 0? What would happen to these solutions of function of t and function of x? So that's what we want to determine. So let's break it into cases. So the simplest case is when lambda is equal to 0. So let's check that out. So case 1. What if lambda is 0? So if lambda is 0, well, our equation 1 becomes t prime over alpha square t is equal to 0. So this is just means t prime is equal to 0. So t is just a constant function, right? By integrating you get t. Well, if t is just a constant function, all right, what happens to the second one? Let's hold on to that, right? Let's look at equation 2. We have x double prime over x is equal to lambda. And now, if lambda is 0, we have x double prime is equal to 0. So what is x of t then? By integrating it twice, you get c1x plus c2. So just to make this constant different, I'm going to call this one just c. Okay, just to make them different. You don't want to call the same constant everywhere. So now let's impose the boundary condition first, and then at the end we'll do the initial condition. So now apply the boundary condition. We have u of 0 t is equal to 0, and we also have u of l t is equal to 0. So at the both endpoints, we're letting the boundary to be 0. So if I apply the first boundary condition, so again, we're not using the function t, we're just using the function x, so I can apply initial condition on, boundary condition on x. So we have x of 0, should be x, is equal to c1, hold on, sorry guys, I need to rewrite this. X of 0 is 0, So that means we have 0 is equal to C2. So C2 is 0. Now apply the second boundary condition. So if I apply the second boundary condition, what happens? So we know C2 is 0, and then so we have x of L now equal to 0, which means we have 0 is equal to C1 times L, right? Because C2 was 0. Well, that means C1 is 0, right? So basically, this function doesn't survive. It's the 0 function. Well, we don't want the 0 function. We want non-zero solutions, right? So this case fails. It doesn't work. So alpha equals 0 doesn't work. Moving on to now, I didn't plug in my initial conditions because if you multiply the 0 function with t of t, whatever that function is, it wouldn't survive anyway. It will go to 0. So case 1 fails. So this one, not important, not needed. So let's go to a second case. So the second case we're going to use is what if alpha is positive, right? So case 2. So we're just going to run down all three cases and see which one survives to give us a non-zero solution. And sometime you'll hear the word eigen solutions. Eigen solutions are just non-zero solutions. So let's look at the second case. We want lambda to be positive. So what guarantees us positive if we do lambda square? So I'm just going to replace lambda with lambda square so that way we guarantee to have a positive value for lambda. Okay? So what does our equation 2 become? So I'm going to take the equation 2 and subtract away lambda x and set it equal to 0. So our equation 2 from above, we have x double prime minus lambda x equals to 0. Well, if we set lambda to be lambda square, then you have x double prime minus lambda square x equals to 0. And then we just solve this ordinary differential equation. So we can write out its characteristic polynomial. We have r squared minus lambda squared is equal to 0. So you have lambda, r is equal to plus and minus lambda. So these are the roots. If these are the roots, then what is x of x? So that's the function c1 e to the lambda t plus c2, sorry, not t, I'm sorry. I keep going back to t for some reason. X, that's the variable, plus c2 e to the negative lambda x. And then what about the first equation? We had t prime over alpha squared t is equal to lambda. So if lambda is positive, then we can write it out with the second function, right? But here's the thing, we can hold on to this. So let's hold on to this. If somehow x of x survives, then we can go ahead and solve for t of t, because if the function x doesn't survive, if it again goes to 0, there's no point of wasting time solving for t, because then we'll have the 0th function for u of xt. So that's why I'm holding on to the first equation. So let's continue with this, apply the boundary condition, and see if it gives us a non-zero solution. So now that we have the solution, now apply the boundary condition. So on the first boundary, we have x of 0, which is 0. So if I plug in 0 for x, we have 0 is equal to c1 plus c2, which means c1 is equal to negative c2. Okay, so we have that. Now let's apply the second boundary condition. X of L is equal to 0. Again, I'm ignoring the t part of the solution because we're holding on to it. So, and this would give us what? So if I plug in L into my boundary, I have 0 is equal to c1 e to the lambda L plus c2 e to the negative lambda L. But we know what c1 is, that's negative of c2, right? So we have 0 is equal to negative c2 e to the lambda L plus C2 e to the negative lambda L. And then what I'm going to do is I'm going to pull out the C2 from here. So we have C2 times e to the negative lambda L minus e to the lambda L equals to 0. Well, this term, if you remember, this is an exponential. It can never be 0. So what is 0 then? C2 is 0. Well, if C2 is 0, then again, this didn't survive, right? Because all of this will just be the 0th function, right? All of that comes down to 0. So there is no need to solve for the t of t equation. So we can now move on to the next case. Now we're hoping that the next case will survive, okay? So we're almost to the end of this derivation. So bear with me for a couple more minutes. Now the last case, this will survive. We're hoping that this will survive so that we have a solution to the heat equation. So the last case is what? Is when lambda is less than 0, meaning we want lambda to be negative. So we have negative lambda square. So that's where I'm going to replace lambda with negative lambda square. So again, I'm going to start with the second equation. If that survives, then we're going to solve the first equation of that ODE. So the second equation, it was x double prime over x is equal to lambda, right? And the first one we had was t prime over alpha square t equals to lambda. So we're going to hold on to this again, the first one. Let's carry on to the second one. So we're assuming lambda is negative lambda square. So we have x square, sorry, not x square, x double prime plus lambda square x equals to 0, because we're assuming lambda is negative lambda square. Now again, writing out its characteristic polynomial, we have r square plus lambda square is equal to 0. So r is equal to plus and minus lambda I. Great. So we have complex solutions for this case. So that means our solution for the x of x, it's going to be C1 cosine of lambda x plus C2 sine of lambda x. So again, we're holding on to the right side. If this survives, we'll use that. Now let's plug in the boundary condition. So let's apply boundary conditions. We know x sub 0 is equal to 0. Plug that in. So we have 0 is equal to, if I plug in 0 into sine, that goes to 0. C1 will survive. So C1 is 0. Nice. So that means my x of x will simplify to this function now. X of x is equal to C2 sine of lambda x. Now I plug in the second boundary condition. X of L is equal to 0. So plug that in. We have 0 is equal to C2 sine of lambda L. Well, now the question is, we don't want C2 to be 0, because if C2 is equal to 0, then everything will fall apart. There is no solution, right? We only have the 0 function to be the solution. So we're going to restrict this a little. So this is what we're going to do. We want sine of lambda L to be 0. Because if that happens, then it is guaranteed that C2 is not 0. Okay? Now, when is sine of an angle equal to 0? Right, so every n pi, this will be 0. So we know if the angle, if the argument is n pi, then we have a true statement, right? So n could be any integer. So let n be any integer. Let's pick positive integers, because you'll see why at the end. So that means now we can solve for lambda. What is this magical lambda? Well, lambda is then n pi over L. That's what this lambda is equal to. So success. We have finally found the function x of x. So x of x is equals to c2 times sine of lambda, which is n pi over L times x. So that was a success. Now that we have x of x, well, now we can go ahead and solve for t of t coming from this one. So we're using lambda is equal to negative lambda square. So plugging that in, we have t prime plus alpha square lambda square times t equals to 0. Actually, we could do better than that, right? If we just keep it on the right side, it will solve much nicer. So let's keep it that way. So negative alpha square lambda square t. And then I'm just going to divide by t, so we have, so I'm just going back and forth. Sorry guys, I should have seen that coming. I didn't. And that's okay. Sometimes we just don't see things, right? Well, now I can integrate both sides and kind of find out what is this t function. So what is this function that will solve this differential equation? Can you guys tell? So if you integrate both sides, you have ln of t, right, is equal to negative alpha square lambda square times little t. And then to solve for this function t, we exponentiate both sides plus a constant. So t of t is equal to e to the negative alpha square lambda square t times the constant c. So that's our function t of t. And now we put this together with our x of x and we have the solution. So hence we have the formula we want. We have, so now the question is, n is going from 1, 2, 3, and so on, right? So that means we have one solution, say u1. That's going to be x of x times t of t. So if I plug in n equals 1, we have a constant c1 times sine of n is 1, so pi over L times x, and the function t, which is, what is the t function? That's e to the negative alpha square lambda square pi, hold on, times t, right? So that's what we got previously right here. So that's like one solution. Now if I let n equals 2, I have another solution. If I let n equals 3, I have another solution. So you can see there are many solutions we have just by letting n run from 1, 2, 3 all the way up to positive infinities, right? So you can see that you have u2, u3, and these are all solutions to the heat equation. Now we want to compile them all together and represent them using the summation notation. So what we have is a general solution, which would be u of xt, and we'll let n run from 1 to infinity. That's what we have the sum for, 1 to infinity. Now, if you realize t of t was this function, c times e to the negative alpha square lambda square t. That was the t of t we computed. But what is lambda we're using? Well, we know lambda is n pi over L. So that's where I'm going to substitute for this piece right here. So if I do that substitution, my t of t will be modified to c times e to the negative alpha square. Lambda is n pi over L, so that will give me n square pi square over L square times t. And then if I put that together in my formula of the summation, we have c1 sine of n pi x over L times the exponential c e to the negative alpha square n square pi square over L square. times t. Well, now if you think about it, this is, you can call this Cn, because n is running from 1, 2, 3, and so on. Now, if I combine these, this is just a constant. This is also a constant. Why don't I just call them another constant that runs from 1, 2, 3, and so on. So I'm going to rewrite it, and then we have our final solution we want. Let's call it a Bn, just another constant. No big deal why I have it as it is. E to the negative alpha square n square pi square over L square times t sine of n pi x over L. So that's the solution I gave you beginning of this lesson, where I said this is the solution you want to memorize. So there you have it. So any questions on the derivation? How do you guys feel? Yeah, right. But it's kind of nice, right? How everything kind of tied together. We were able to use our knowledge from separation of variables, from ODEs, and then we were able to separate this PDE into two ODEs, and then we broke Lambda down into 3 different cases, and we only took the one where the constant survives, because if they go to 0, then we have no solution. And then once we found the case that we want, which was the third one, where lambda is less than 0, we went through the entire calculation of solving for this function x of x, because that's one of the functions that we're going to assume the solution has. And then once we have that, we solved for the function t of t, and that happens to be the exponential function. And then now we put all of these together, because we said that our assumption that our solution is the function x of x times t of t. So we put both pieces together, and because we saw that as you let n run from 1 to infinity, you have so many solutions. So just to compile all of them together, we express them as a summation. So if you remember from 4.1, where we didn't talk about the nth order differential equations, so because U1 is a solution, U2 is a solution, which means their linear combination will also be a solution. So therefore, we write down all of that using the summation. So the linear combination of all of these solutions will give us a solution as well. So why not, right? Put them as a summation. So I forgot to write n equals 1 to infinity. Now the next question, what we haven't done yet is we haven't applied the initial condition, right? So all of this was up to the boundary condition. So what was the initial condition, guys? So if you go back, all of that was up to the boundary condition. Now let's impose the initial condition and see what will this modify to. So our initial condition is u of x when t is 0, you have some function f of x. Well, let's check it out. What is that? So if I apply the initial condition now to my final solution, I should have, what is this unknown constant, Bn? So we have u of x 0 is equal to some function f of x. So we have f of x is equal to, so plugging in t equals 0 and x is x, we have the sum from n equals 1 to infinity of Bn. So t is 0. So the exponential term will have value 1. Then you have sine of n pi x over L. Well, this should ring a bell. What does this remind you of? So it's odd, right? Odd. Right, because you have sine, so that should tell you it's an odd function. So that f of x for the initial condition will always be an odd function, because for this to work, you have to use an odd function. So what is Bn? Well, Bn is the same coefficient from the Fourier sine series. So we can say that the Bn is the same coefficient from Fourier sine series. So what is Bn? Well, we know Bn is, so in Fourier sine series, we use the little bn, right? So let's use that. So this Bn is really that little bn from the Fourier sine series, which was given by 1 over L integral from negative L to L f of x sine of n pi x over L dx. Well, because now the function is odd, sine is also odd, their product is even, so I can double this integral. This is 2 over L going from 0 to L f of x times sine of n pi x over L dx. So that's your Bn. So there you have it. So any questions on this? Now, if you, so let me know if you guys have questions, okay? So if you realize heat equation will always be two-part question on the final or whatever exam, because if you want the coefficient to apply the initial condition, you have to know what is the Fourier series for that particular function. And then by having the same coefficient that you computed, you just plug it into your solution right here. So Bn is what's unknown to you. So you'll plug this in from Fourier sine series. Alpha square will be given to you in the problem, and then n will just run from 1 to infinity. L should also be given to you in the problem, and that same L goes here. So the ones that I boxed are the unknown variables that you're going to plug in from the question, and Bn will be determined from the Fourier sine series. So you can see that for heat equation, you will always have Fourier sine series, not cosine series. So that wouldn't be useful for this particular example. Now, let's do an example with this. So that way you know at least how to use this formula. But the key idea is to memorize this formula. And if you ever forget, well, you know separation of variables, know how to use it, okay? All right, having said that, let's do a problem. So I did crop some question here. Ooh. Okay, let's do this one. This is cool. So this was one of the questions given on the past final. And you'll notice that it's a two-part question. So the first part is to find the Fourier coefficient. And the second part is to use that for the heat equation, because both are related. So here's part A and B to this question. So check this out. So the first part is what we did on chapter section 10.2, 10.4. Compute the Fourier series, right? Now, in this part, it says compute the Fourier sine series. So automatically, you know this is going to be an odd extension. So that gives you a hint. So you know that A0 is going to be 0 and AN is going to be 0. So what you're looking for is Bn. So you write out the Fourier expansion once you find your Bn, and using that same Bn, you'll do part B. Part B is to find the solution u of xt for this differential equation. And, ooh, there's a typo in the question. So this should have been 1, right? It's the same L from part A. Yep. Okay, so do you guys see where this is going? Any questions on this? Are you guys following? Okay, so first we're going to do just plain Fourier series. Let's find it. So if you want, you can do the drawing, but you don't have to. It's not required. So I'm going to go ahead and draw this. So when x is 0, the function is at 1. That's right here. And then when x is 1, the function is at 0. So it's a parabola right here. So just that tiny piece. Now you want to extend this as an odd function, but we need 2L first before we do that. So I'm going to draw the other half of this function, extend it as an odd function, so it will look something like this. So this is -1, -1. So that's how the odd function would look like. Now let's extend this. So copy paste on both sides. So we have something like this. And then, okay, so let me see how I would draw this. Right? Something like that. And then on the left side, you do the same thing. So you see how that's the extension of this function. And in the Fourier series, what it would do, it will connect all of this with a smooth wave. Ooh. Ooh. Something like that. Hopefully that makes sense. So let's find that white function, right? That white drawing that I just drew. So we know A0 is 0, AN is 0, so we just have to find BN. So part A. So BN is going to be 1 over L integral from -1 L to L f of x sine of n pi x over L. Well, our function is odd. We extend it as an odd function, and sine is also odd, so the product is even, so we can do 2 over L integral from 0 to L f of x sine of n pi x over L. So what is L in this problem? What is L, guys? It's 1, because so this is from 0 to L. So L is 1. And this is 2L. That one period is 2L. So half of it will be 1. Or you can always look at the interval that's given to you. So if you look here, this right here, so this is 0 to L. So L is 1. So there are multiple ways you can determine the value for L. Okay, so now we have L. We know f of x. Plug this in and integrate. So 1 over 1, that's 1. Oh, I'm doubling the integral, so I have to write 2 over 1. Times 0, the integral 0 to 1. F of x is 1 minus x squared times sine of n pi x, because L is 1, dx. So we have some integration by parts to work on. So let's do it. So we're going to use the tabulars method again. So we're going to differentiate in this column and then integrate on this column. So 1 minus x squared, differentiate -2x, differentiate again, -2, differentiate again, 0. And now integrate sine of n pi x. So help me out. What is the integral of sine of n pi x? Negative cosine of n pi x over n pi. So make sure you guys are checking your work with me, because it's possible I might make a mistake somewhere. And then if I integrate again, I get negative cosine of n pi x over, oh, sorry, you see already, I started making mistake. So this is negative sine of n pi x over n squared pi squared. I think that's right. Integrate one more time until you reach the 0th level. So, so I should get cosine of n pi x over n cubed pi cubed. So someone double check my integration. I think they're right, but just double check. I think they're right. Any questions on this? Okay, I think they're right. Let's go. So we cross them this way, and then we multiply with plus and minus. And let's write those out. So we have 2 times all of those. So we have 1 minus x. Okay. Yep. All right. Hello, hello, hello. Can you guys hear me? Okay, thanks. All right, so the first one we have negative times that cosine of n pi x over n pi, taking it from 0 to 1. And then the next one we have minus minus minus, so that's 3 minus 2 over 2x over n square pi square sine of n pi x going from 0 to 1. And then one more, we have negative cosine of n pi x over 2 n cube pi cube going from 0 to 1. So there you go. Now let's evaluate these. So a lot of them should go to 0. That's what we're hoping. But let's see what happens, right? So for the first one, for the first term, as you plug in 1, 1 minus x squared goes to 0, so everything will go to 0. And then minus cosine of 0 is 1, so what I will be left with is plus 1. Cosine of 0 is 1, so that will be 1 over n pi. So again, double check my work, guys. 2 times that. So all of that is on the first term of this result. Now for the second one, we have plug in 1, sine of n pi will go to 0. Plugging the bottom limit, so I'm looking at this one now. Plug in the bottom limit, that will also go to 0. So all of that is 0. Now let's look at the last one. If I plug in 1, I have cosine of n pi, so that would survive. 2 times negative 1 to the n, because cosine of n pi is negative 1 to the n. And on the bottom we have n cube pi cube. And now I plug in the bottom limit 0, so minus minus plus 2, cosine of 0 is 1 over n cube pi cube. Okay, that's pretty, right? That's not so bad. So now if I just continue and simplify this further, but we have our coefficient bn, so that's bn. Let's simplify this more because we can. So if I let n run as even and odd numbers, this would simplify. So if n is even, so let's write it out as a piecewise. If n is even, we have 2 over n pi minus, so negative 1 to the even power, it's going to be positive, so that minus and plus 2 over n cubed, so they will cancel out. So the remaining parts are going to be 0. So if n is even, the coefficient is only 2 over n pi. And if n is odd, what happened to these coefficients? So if n is odd, we can combine them, right? So we have 2 over n pi plus 4, that's 8 over n cubed pi cubed. So I was able to combine these pieces with the even power and odd power for n. So they combine nicely. Now, for this question, I would just leave it right here, because if n is even, you have that as a coefficient for bn. If n is odd, we have the bottom one as the coefficient for bn. So these are the value for bn. So now we're almost ready to write out our solution. And even n, we're going to represent it as 2n, and odd n, we're going to represent it as 2n minus 1. So what is our Fourier series for this function? Well, that's going to be f of x equals, so a0 was 0, an is 0, so we only have bn surviving. So we have n equals 1 to infinity bn sine of n pi x over L. Now let's plug in what is that bn. We have the sum from n equals 1 to infinity. Now we split it up into even and odd, so for so let's just think through this question. Can we simplify this more? So do you guys see any error anywhere on my integration? Yeah, right? Okay. Alright, so let's trust that. I'll trust that. I feel like something went wrong, but I can't catch it right now. But to me it looks fine right now. Let's just continue. So we're gonna split it up into two different cases. So for n is equal to even, so for odd we have 2, so bn is going to be 2 over n pi. And again, if you want to combine this as a using common denominators, you can do that, but I wouldn't. So I'm talking about this one right here. If you want to combine that using common denominators, you could. I wouldn't do it for now, but let's just write out the answer. Over n cube and pi cube. So that's bn sine of n pi x. Oh, actually, I don't want to write it like that. I'm going to write it this way because we're using n as odd. So bn is going to be 2 over 2n minus 1 because n is odd, pi plus 8 over 2n minus 1 to the third power, pi to the third, that's for the odd coefficients, times sine of n pi x. And then for the even coefficients, we have 2 over n pi times sine of n pi x. So that would be our formula for this. Now this looks really messy, so because of that, I'm actually going to use this part of the bn because this looks much more simpler than actually writing the piecewise definition out. So let's just use that. So let's ignore that part. So you can ignore this. So most question it will simplify to something nice. For some reason this example I picked, it doesn't simplify nice. So I'm just going to use that formula and write out the solution. So ignore that. So keeping the initial bn we computed, our solution, the Fourier series would be 2 times that. So that would be 2 over n pi minus 4 times negative 1 to the n over n cubed, so plus 2 times 2, that would be 4. 4 over n cubed pi cubed times sine of n pi x. I'll leave it like this because it looks like if you split it into cases for odd and even n, it doesn't really get any simpler than this. So ignore the one on top. This is good enough. Our coefficient for bn is this huge, but sure, right? Why not? Let's keep it. So any questions on this? All right, so that's the answer to part A. Now for part B, all you have to do, use the Bn that you computed for part A, plug it into the solution of the heat equation. Now from the heat equation, what is your alpha square? What is that value? The thermal diffusal value. So this is the heat equation, right? You have U sub T 49, right? Alpha square U sub XX. So this is our alpha square. And then L, we know L, that's 1. And we already know Bn, that's from part A. So we just plug all of that into our formula. So for part B, all you have to do is substitute. We know alpha square is 49 just from the formula. We know L is equal to 1, and we know Bn is equal to that giant formula we got. Oh boy. I feel like something went wrong with that problem. But let's just continue for the remaining time. So we know that's Bn. Right? And all of these we're going to substitute into our solution for the heat equation. So the solution is the formula, the infinite sum, n from 1 to infinity, Bn. So I'm going to use the little bn, but that bn is the big Bn we wrote down in the formula, e to the negative alpha square n square pi square over L squared times T sine of n pi x over L. So let's substitute the unknown. So hence our solution to this heat equation is going to be the infinite sum n equals 1 to infinity. Bn is where we computed 2 over n pi minus 4 times negative 1 to the n plus 4 over n cubed, pi cubed, times the exponential to the alpha square. Well, alpha square was 49, and n square, pi square, L was 1 times t times sine of n pi x, because L is 1. So that will be our solution to the heat equation. So all I did was substitute, because there's no need for you to derive the formula on the test, because we already seen the derivation. We know how the solution looks like. It's going to vary depending on what the material of the rod is made out of. And that coefficient, the thermal diffusibility coefficient, will always be given to you on the question. L is also given to you, and Bn, you will compute it by the Fourier series of that particular function that's given to you. Any questions on this? Does it make sense, guys? Oh yeah, right. So that 8 point is worth it, right? Okay, so I want to do one more example on separation of variables for PDE, and then we can, if we have time, we'll do another problem on heat equation and Fourier series. But for now, let's just do another problem on this. So here's another problem on separation of variables. So just applying the method for PDE. So this was also given one of the past final exam. So you want to use the method of separation of variables to replace the PDE with two ODEs. So just like we did for the derivation of the heat equation, but now you just want to write out those ODEs without really solving for them. So we're going to assume the following, right? Again, assume that our solution is a function of x and a function of t. Okay, so that means I can differentiate this partially and plug it in. So just for simplicity, I'm going to write x times t as the big function variables. So u sub t is going to be x t prime, because x is a constant, and then u sub, so you see your differential equation requires uxx, uxt, and ut. So we're going to compute those derivatives, plug them in, and then use the separation of variables. So u sub x is going to be what? Well, let's do u sub xx, right? So that's just computing the second derivative respect to x. T is a constant. And then u sub x is going to be x prime t, and then u sub x t, well, that's going to be differentiating ux by respect to t now, so that's x prime t prime. So we're going to plug in this into the differential equation, and this, and that, and see if we can use the separation of variables. So plug it in. So we have uxx, that's x double prime t, plus 5 uxt, that's going to be x prime t, minus ux, that's going to be x t prime, equals to 0. So I just took the derivatives, partial derivatives, and then plug it into the differential equation that's given to you, and now just play around with it. You want a function of x equals to a function of y. Sorry, not y, t. Keep forgetting the variables. So just stare at this and see how you can isolate. What can we do to kind of separate these variables? So I'm going to go ahead and divide by t. I think that will do it. So you just have to play around with it and see if it works. If I do that, I have the following. I have x double prime plus 5x prime t, right? Yeah. Yeah, thank you. Yeah, it looks so weird. Okay, thank you. Now it makes sense. Okay. Over t, and then minus xt prime over t equals to 0. Alright, so that looks like a good step. Now, what can we do next? So, let's see. So I'm going to go ahead and move the last two terms on the right side. So then I have the following. X double prime is equal to x t prime over t minus 5x t prime over t. So I just moved them to the other side. Well, now it looks like I can do some factoring, right? So I factor out the t prime over t, and I'll be left with x minus 5x. X is the variable, okay? The dependent variable in this case. And now I can successfully divide by my function x minus 5x, right? So that would give us x double prime over x minus 5x is equal to t prime over t. And the only way these two functions can be equal if they equal to some constant lambda. So now we, what did I miss? X prime. Thank you. Got it. Thank you. Appreciate it. So now we have the two ODEs almost written out. So the one, you have x double prime over x prime minus 5x equals to lambda. And if you isolate this, this would just be x double prime minus lambda times x prime minus 5x equals to 0. So that's one ODE. And the second ODE we have is t prime over t is equal to lambda. So that would give us t prime minus lambda t equals to 0. So there you go. We have two ODEs for the given PDE. So any questions on this problem? All right, so we were able to finish the course successfully. We finished the derivation of the heat equation, so that's the magical formula I wrote down all the way up here. Make sure you remember this formula for the final. And also remember that Bn is the same coefficient for the Fourier sine series. So the example I did was a bit complicated. Uh, it just took us a really long time to get through it. But I will do more problems with you guys on the review session, so just make sure you come for the review. We'll do tons of examples, so all of these concepts that we run through will make more sense to you. For now, we'll finish the lesson here and we'll pause. I do want to mention that all right. Okay. Is this better? Yeah. Okay. Thank you, guys. Thank you. So, for the final exam, you are required to submit your work like you've been doing for the exams. I will send out a Dropbox link. Okay. Okay. All right. Hello. Hello. Guys, can you hear me? Okay. All right. Let's hope it will work for next few minutes. So I will send out a Dropbox link. So your exam is from 5 to 7:15. So uh, all right. So let's do oh boy. So let's put the deadline for submission 8 p.m. Okay. So the deadline to submit your work as a PDF file. So PDF file should be hand in by 8 p.m. So 7:15 you finish. You got tons of time to submit those work. So that's the last thing I want to say. So I want to thank you all for being here, and hopefully you enjoy the course with me as much as I have enjoyed it with you guys. So hopefully we'll see each other in the future when our school opens. Maybe we can see each other, come by, say hello. I'm in the next building, 6th floor, 6271. That's my office. If you ever want to stop by, you'll find me there. Or send me an email, whatever pleases you. So I hope to see you guys all on Monday and Tuesday for the review session, so we can do a lot more examples just to catch up with some of the things that we didn't get to cover in class, which is more likely examples. Any questions from you guys? Yeah. So if you look at the question, right, you're only given half of the period, which is 0 to 1. So that half is 0 to L. Because if you look at the picture for the Fourier series, we always go from negative L to L. So if you're only given this portion of it, that's already half of the period. Does that make sense? So if you look at the interval, it gives you 0 to L. So that's what I wrote down right here. This is 0 and this is L. So you can kind of correspond those values. 0 to L, 0 to 1, L is 1. And if you're given the entire period 2L, then you take that period and then you divide it by 2 to find the value for L. So for example, if I give you the interval, so let's go back, right? If we go back to the first example we did today, which was this one, right? So you're looking at negative 1 to 1. So this is your length, negative L to L. So how do we find L? Well, L will be the half of this period. So if you do 1 minus negative 1, that's 2. So that's 1 period. 2L is equal to 2, so L is 1. So you can always kind of line them up like that and then determine the period. Or you can draw the picture and then find the period 2L and divide it by 2 to find L. Does that make sense, Sadia?
Yes.
All right. Any other questions? So I don't know how many questions on the final. I haven't seen the final exam. So Professor Aiken is the one who's making the final. So who knows, right? We will wait and see what he has for us. All right. So this is it, guys. Thank you all for being here. I hope you guys enjoy the course. I hope all of you do well on the final and hopefully be successful in the future courses as well. And I wish to see you all on the review session, so hopefully we'll see you there. So this is the end of our lesson for today.